So this is the video on simple harmonic motion. So this topic mainly revolves around springs and pendulums and basically anything that symbolizes periodic motion. So basically the position function of an object in simple harmonic motion is basically this. It would be most commonly this one. We know that A is the amplitude, omega is the angular velocity, and this is not even necessarily shown in the equation. It's the phase constant, which is basically how far you started from your zero position. So if you started at 0 here, then theta would be the phase constant. It's an angle, basically. And this is just something you need to pay attention to. Frequency is the inverse of period, the t is period. And essentially, this is basically the equation for period, and this is the spring equation. It uses the m over k, so the mass over the force constant of the spring, also known as spring constant, but since it's present in pendulums, people will refer to it as the force constant. So this equation of the period, it doesn't depend on the acceleration of gravity or the amplitude. So it's basically the same thing for the pendulum period. It doesn't depend on the mass or the amplitude. So here you have the length to the center of mass, which is usually just like here. Or if it's like an object or something, it's going to be somewhere else. This one actually depends on g. So this situation is only true if it is a simple pendulum, which by definition is a pendulum that makes an angle of less than 10 degrees at its highest amplitude. So if you have a spring with a mass sliding like this, you have that potential energy is equal to 1/2 kx squared, and the kinetic energy at any moment is equal to 1/2 mv squared. Well, we all know this. This is just the standard kinematics equation for kinetic energy. So the total energy, which would be the total potential energy over here, where the kinetic energy is 0, or the total kinetic energy over here, which would have no potential energy, it would be 1/2 ka squared, and a is just the amplitude distance, so it's just like that. So you can actually use this equation to solve for the maximum kinetic energy of the object, and therefore the maximum velocity if you ever have to. So here's some equations for the angular velocity and acceleration, or rather the linear velocity and acceleration. So it's pretty obvious, it's just the derivative of x. So essentially, to get the derivative, you probably already know this, but in case you don't, now you would take the constant out of here, and essentially you just move it here, and the derivative of cosine is negative sine. Derivative of negative sine is negative cosine, and then you take that out again, so it would be omega squared. So yeah, that's the three equations. And again, keep in mind that the only time that a pendulum is a simple pendulum is if it is making an angle of less than 10 with the normal. So here are the graphs for the displacement rather, velocity and acceleration. So essentially here you kind of start out at the maximum distance, or rather the maximum amplitude, and so it kind of changes here. So when you reach the maximum velocity, it reaches 0, so I guess if you look at it like this, it would reach here, where it would be 0, and here would be like the top amplitude. Right here, where the, so basically right here where essentially the displacement starts going back up, it essentially shifts, and that's where the derivative would be equal to 0, so that makes sense. It's kind of hard to see from these since I didn't put them in one column, but basically that's the relationship here. And basically right here, where the velocity switches from increasing to decreasing, is when the acceleration is 0. So basically the force going, there is basically no force in like a direction either left or right. So another thing to keep in mind about springs is if they're connected in series or parallel. So if you've done any electrical physics, this probably sounds familiar. Here they're in series, and basically springs behave just like capacitors do, or the opposite of resistors. So if you have a K constant 1 and K2, then in series they would be 1 over the effective K equals 1 over K1 plus 1 over K2, and so on. So, yeah, like resistors in parallel and capacitors in series. And here in parallel, K1, K2, you literally just add them up. So, yeah, that's just about it for simple harmonic motion. So, here we have an interesting AP problem. I find it interesting because it's really conceptual, and like you can see, it had to write a whole paragraph over here and another paragraph over here. And that's just about it for the math. Alright, so here, this is problem 2009 it's the second problem in the mechanics exam for 2009. Here's the diagram. It's basically a bar, rectangular prism kind of thing. So, and basically it's allowed to swing on this cylindrical bar. X is the distance to the center of mass, and L is just the length of the bar. So, part A is asking you to write the differential equation for the angle theta that the bar makes with the vertical. So, essentially, it's asking you to find where the maximum amplitude angle would be, like that. So, it's kind of ugly, isn't it? Well, I tried. So, basically, okay, so the torque would be negative mgx sine theta, since essentially when the thing is swinging up, the torque is going against it. So, this is the force of gravity times the radius, and you also have to find the force that's perpendicular to the bar, so you have to multiply it by the sine of theta. That's equal to I alpha. So you know that alpha is essentially, it's the second derivative of displacement, and since displacement describes the change in the angle, it would be the second derivative of time with respect to theta. So that's the answer to part AI. Part A2 asks you to use the small angle approximation to calculate the period of the bar's motion. So, this is an important point. The small angle approximation relates to the angle of a simple pendulum, and essentially what it says here is that theta as a radian becomes pretty close to the sine of that radian, and yeah, essentially any trig of that radian would basically just become theta. So essentially you can literally say that sine theta is equal to theta, and you simply take this equation, put that in here. So if you divide both sides by I and use the same technique for A, plug that in here, we have this. And since this is this is what describes simple harmonic motion, we could just look at this and say that omega squared is equal to this thing right here. So we can say that omega equals the square root of mass times g times x over the moment of inertia. So we also know this basic equation for period, and we simply plug it in. So there we have this. So part B is related to A2. So it's asking us to describe an experiment which we would use to determine the moment of inertia. And we also have to account for experimental error. We basically have to minimize it as much as we can. So since we know this equation, like, all we know that we know m, we know x, we need to find I, and the only thing we don't know is t. So we would have to measure it. And to measure t, which is simply the time it takes for the pendulum to make a full swing, we would need to simply time a swing. We could just time one, but that wouldn't be very accurate. And since the time remains the same for a pendulum, even if it eventually starts slowing down, so it can have a pretty big distance that it travels, and it eventually might just slow down to become something like this, the time will still stay the same. So if you go through about 10 swings, you'd get some pretty accurate results. All you have to do is measure the time for 10 swings, divide it by the 10. Or if you want to be more accurate, go for a lot more swings and divide it by that number. So, yeah, pretty much that explains it. Then you plug in the value for t and mx, and you would solve for I. Or, of course, a better way to do it would be to solve this equation for I and then plug it in. So part C, the final part, is also an open-ended question. And it's asking you to experimentally determine the center of mass, assuming you don't know it. So this is an even less of a mathematical question. It's literally asking you to use the two-finger rule, essentially, but with a fulcrum. That didn't work. So you place this thing on a fulcrum, and if it leans left, then you move the fulcrum to the left, and if it leans to the right, then you would move it to the right. And if it stops, then you found the center of mass. So that's basically all you have to write here. You get full credit on the AP exam. So yeah, that's pretty much it for this problem.